Problem number 21. A syringe is filled with water of density ρ and negligible viscosity. Its body is a cylinder of cross-sectional area A1, which gradually tapers into a needle with cross-sectional area A2 much less than A1. The syringe is held in place and its end is slowly pushed inward by a force F, so that it moves with constant speed v. Water shoots straight out of the needle's tip. What is the approximate value of F? Solution to problem number 21. If the water has speed v' when it leaves the needle tip, then A1v equal A2v'. The water outside the syringe has atmospheric pressure, so by Bernoulli's principle, the pressure P of the water inside the syringe obeys equation 1. The required force is the area times the pressure difference. That was answer D. Incidentally, if you don't know Bernoulli's principle, you can also solve the problem by equating the power, Fv, with the rate of change of kinetic energy of the water. This was the solution to problem number 21. Problem number 22. A spherical shell is made from a thin sheet of material with a mass per area of sigma. Consider 2 points, P1 and P2, which are close to each other, but just inside and outside the sphere, respectively. If the accelerations due to gravity at these points are g1 and g2, respectively, what is the value of absolute value of g1 minus g2? Solution to problem number 22. Suppose the shell has radius r. By the shell theorem, the gravitational field vanishes inside, so g2 equals 0. The gravitational field just outside has magnitude g1 equals gm over r square, where mass m equals 4 pi sigma r square is the total mass of the shell. Thus, the unknown variable r cancels out, and the answer is 4 pi g sigma. That was answer D. Note that this is actually a universal statement. Above, we found that it didn't depend on the sphere's radius, but more generally, it is true regardless of the shell's shape. The reason is that g1 minus g2 is solely determined by the mass near P1 and P2, and if one zooms in enough to a patch of any surface, then it always looks like an infinite plane, so the answer doesn't depend on the shape of the surface away from that patch. This was the solution to problem number 22. Problem number 23. Collisions between ping-pong balls and paddles are not perfectly elastic. Suppose that if a player holds a paddle still and drops a ball on top of it from any height h, it will bounce back up to height h over 2. To keep the ball bouncing steadily, the player moves the paddle up and down, so that it is moving upward, with speed 1 meter per second whenever the ball hits it. What is the height to which the ball is bouncing? Solution to problem number 23. In the reference frame of the paddle, the ball loses half its energy during the collision, so the speed of the ball immediately after the collision is 1 over root 2 of its speed immediately before the collision. Let v be the speed of the ball relative to the ground immediately before the collision, then we have equation 1 to find speed of the ball right after the collision in our original frame of reference. From here v equals 5.83 meters per second. The height of the bouncing is v square over 2g, which is 1.7 meters. This is the answer D, and that was solution to problem number 23. Problem number 24. When a projectile falls through a fluid, it experiences a drag force proportional to the product of its cross-sectional area, the fluid density ρf, and the square of its speed. Suppose a sphere of density ρs much greater ρf, of radius r is dropped in the fluid from rest. When the projectile has reached half of its terminal velocity, which of the following is its displacement proportional to? Solution to problem number 24. During the fall into the liquid, gravity and braking force are applied to it, described by equations 1. Since the mass of the body is expressed by formula 2, and therefore acceleration is the derivative of velocity with respect to time, gets a simple differential equation with separable variables 3, through which the dependence of velocity on time is observed. Here the coefficient beta is expressed by formula 4. Next, since time is expressed through distance and velocity by formula 5, we can use it in formula 3 to display the dependence of distance on velocity through formula 6. This formula is easily integrated as 7. Next, using the expression for terminal velocity 8 and the expression for half-terminal velocity 9, we get the final answer in the form of 10, which gives us the distance dependence on densities and radius in the form of an answer B. And this was the solution to problem number 24. Problem number 25. A yo-yo consists of two massive uniform discs of radius are connected by a thin axle. A thick string is wrapped many times around the axle, so that the end of the string is initially a distance r from the axle. Then, the end of the string is held in place and the yo-yo is dropped from rest. Assume that energy losses are negligible and that the string has negligible mass and always remains vertical. Below, we show a cross-section of the yo-yo partway through its descent, between the moment the yo-yo is released and the moment the string completely unwinds. Which of the following is true regarding the yo-yo's acceleration? Answer A. It is always 0. Answer B. It points downward, but decreases in magnitude over time. Answer C. It points downward and has constant magnitude. Answer D. It points downward, but increases in magnitude over time. Answer E. None of the above. Solution to problem number 25. As the string unwinds, the radius small r of the string remaining about the axle decreases. Specifically, if the yo-yo has fallen a distance c, and the string has total length l, then small r square over big R square equal l minus c over l. This change in r affects how the energy of the yo-yo is divided between translational and rotational motion. If the disks have total mass m, conservation of energy gives mgz equals 1/2 mv square plus 1/2 I omega square, where I equals 1/2 m big R square. But omega equals v over small r. Solving for v gives formula 1. We can equalize first derivative to this expression by z to 0 to find that maximum is around z equals 0.6 L. Intuitively, in the beginning the yo-yo has roughly constant acceleration downward, but as the string unwinds, more of the energy goes into the yo-yo's rotational motion. In fact, the translational speed of the yo-yo goes to 0 when the string completely unwinds, at which point it's just spinning in place. Therefore, during the latter part of its fall, the yo-yo has upward acceleration, so the answer is none of the above. Which is answer E. This remains true regardless of the details of the yo-yo, because it only depends on the fact that the radius, small r starts equal to big R and then becomes very small, since the axle is thin. In particular, changing how small r depends on z, or the moment of inertia of the disk, won't change the answer. And this was the solution to problem number 25.